In many inferential procedures, there are necessary conditions that must be satisfied in order for our sampling distribution of our estimators to be appropriate. And an important consideration in any analysis is to examine whether or not these conditions hold. For confidence intervals, if these conditions don't hold, we can't claim that the confidence intervals have the coverage that we say they do. Without the necessary conditions, for example, we can't say that a 95% confidence interval covers the true theoretical parameter for 95% of all data sets. The actual coverage might be much less. In this video, we'll take a closer look at the necessary conditions we need for the two types of confidence intervals we've covered so far. For a confidence interval for a proportion, or for the probability of getting a success on some experiment, we have this formula. And for that p in the margin of error, we saw that we can either plug in our estimated value p hat, or if we want to be a bit conservative, we can plug in 1/2. The construction of this formula required two conditions to hold. First of all, we needed all n observations to be independent of each other. So, say we were estimating the probability of getting a red when flipping a beer cap, we need each flip of the beer cap to be independent. If we're estimating the proportion of Torontonians who support the job that their mayor is doing, the people polled must not be related. This independence condition is hard to check using statistical methods, but it's extremely important to think about the context of the problem and whether or not it applies. For our second necessary condition, we note that the formula also includes the quantity Z alpha over 2, which is a critical value from a normal distribution. As we saw, p hat can be thought of as an average, and in order for this formula to be appropriate, we need n, the sample size, to be large enough for the central limit theorem to kick in so that p hat is approximately normally distributed. We'll now investigate the effects of this second condition on the coverage of a confidence interval. We'll use this applet, which simulates data and calculates the resulting confidence interval for any value of the theoretical parameter p and any sample size n that we want. In this applet, the Greek letter pi is used for our theoretical parameter that we've been calling p. Let's start with an example that we're quite familiar with now, flipping a coin that's equally likely to come up heads or tails 10 times. So we'll keep pi at 0.5, that will be our probability of heads or our probability of getting a success, and we'll change the sample size n to 10. Our first random simulation of this gets 6 successes and 4 failures, so p hat, our proportion of successes, is 0.6. We can see the sample we got here in this box showing the 6 successes and 4 failures. Throughout, I'm going to stick with a confidence level of 95%. Using our formula, the confidence interval is from 0.296 to 0.904, as we can see here in the applet. The vertical bar is our theoretical parameter. The applet draws a confidence interval from its lower to its upper limit, and if it crosses the vertical bar, then the confidence interval includes p. And we can see that this confidence interval from 0.296 to 0.904 includes 0.5, and the confidence interval crosses the theoretical bar. So this confidence interval captured the theoretical value that we're trying to capture. Let's try another sample. Again, we get 0.6 for the proportion of successes. Let's try it again. This time we get 8 out of 10, a less likely value. And we now have a confidence interval that does not include 0.5. It doesn't cross our vertical bar, so it gets colored red. So far, 2 of our 3 simulated confidence intervals have done what we want them to do. That is, they include our theoretical parameter p of 0.5 in between its limits. To better see how well this is working, let's simulate 100 such confidence intervals. Confidence intervals aren't designed to be perfect. Indeed, they're designed to miss a certain percentage of the time. And since we're doing 95% confidence intervals, we expect our confidence interval should miss 5% of the time if it's appropriate. So in the 100 confidence intervals we're simulating, and assuming that the necessary conditions are being met, we'd expect that 5 of them would not include 0.5. They'd miss our theoretical parameter. And here are our 100 confidence intervals. We can see all of the 100 estimates of p-hat in this plot. The estimates marked in red are the less likely values, and they correspond to the red confidence intervals, which don't include 0.5. There are 15 of these red confidence intervals, so we've only captured the true value of our theoretical parameter 85% of the time, instead of the 95% that the confidence interval was designed for. Did we just get unlucky? Let's try this again with another 100 simulations of these 10 coin flips, and we get 84% of our confidence intervals capturing the true parameter. Again, less than 95%. So it seems that a sample size of 10 isn't enough to rely on the central limit theorem normal approximation for the sampling distribution of p-hat. What if we flipped our coin 100 times? Will the normal distribution be a better approximation to the distribution of p-hat than it was for n flips? Let's try 100 simulations again. This time, 94% of our confidence intervals included 0.5, which is very close to the 95% that we expected. And one more time, we get 94% again. So it seems that a sample size of 10 wasn't sufficient, but 100 looks pretty good for our central limit theorem approximation, at least when our theoretical value of p is 0.5. When the probability of getting a success is 0.5 or 1/2, the sampling distribution of p-hat is symmetric, centered around its expected value, 0.5. Here's the distribution when n equals 100. But regardless of the sample size, the shape is symmetric with a strong central peak, both features of the normal distribution. When the theoretical parameter p is closer to its limits, let's look first of all at, say, p equals 0.05, so the probability of success is only 5%. Then the sampling distribution of p-hat is skewed, unlike the normal distribution. And as you might expect in this case, we need a larger sample size before the normal approximation works well. Let's investigate this with the applet. We'll change the theoretical parameter to 0.05 and take 100 samples, each of size 100, and calculate the confidence interval each time. These are squished over to the left now because we're trying to capture 0.05, small value on this scale. Instead of 95% of our confidence intervals capturing 0.05, we got 90% of our confidence intervals capturing our theoretical parameter. Let's try again, get 90% again. Let's see if this is a fluke. Try another time, 91%. And once more, this time 88% of our confidence intervals capture our theoretical parameter. So it seems that the coverage of these confidence intervals isn't bad, but it's not the 95% that we claim. Let's try something even more extreme. This time we'll make our probability of success 0.01, only 1%. The sampling distribution of p-hat, then, is quite skewed. With a sample size of 100 and a probability of success of 0.01, only 59% of our sample of 100 confidence intervals capture the theoretical parameter. That's not very good. Let's try again. This time, we get 66%. Still not very good. So clearly, something's not working with our confidence interval. For a theoretical p that's so extreme, only 1%, 100 is not a sufficient sample size for our normal approximation. So now let's try bumping up our sample size to 1,000. Now this time, 94% of our confidence intervals captured the theoretical parameter, very close to the 95% claimed. So for such a small theoretical p, a sample size of 1,000 is at least sufficient. The normal distribution is a continuous distribution, yet in this case, we're using it to approximate a discrete distribution, discrete since we can only get an integer number of successes. So the confidence level is often less than 95%, or whatever level is chosen, because the normal distribution isn't a perfect approximation. Many improvements have been devised for this method of confidence intervals for p, including 2 that are implemented in this applet that provide more accurate coverage. It's also worth noting that these confidence intervals are designed to account for the imperfections we have because we only have a finite sample of data. And if we had a different sample, we'd likely get a different estimate. In polls, there are often many other sources of error, such as non-response bias and the error that results from poorly worded questions, and we haven't accounted for any of these sources. Now let's switch to our second confidence interval, this time for our mean, where we have this formula. The necessary conditions for this confidence interval to hold, in other words, for this confidence interval to truly capture the true mean the right percentage of the time, are first of all, that the n observations are independent. Again, independence is difficult to check, but there's no way around this one. You can think of it this way. If the n observations aren't truly independent, then your sample size really isn't as big as n. It's something a little bit smaller, and thus that formula doesn't apply. Our second condition is that we need x bar, our estimator, to be approximately normally distributed. And we'll investigate how well the central limit theorem works in this context, by how well our confidence intervals work. Again, we'll use an applet where we start with a theoretical model and simulate several confidence intervals to see how often we capture the true theoretical mean within the confidence interval. This time, we'll start with a normal distribution. This normal distribution has a mean of 500 and a standard deviation sigma of 100. 500 is our theoretical parameter that we want to estimate, and it's marked by the vertical bar below the histogram. We'll also work with a sample size of size 10. We'll take a random sample, and you can see in yellow the sample values that were selected to be our data. For this sample of size 10, the average, x bar, which is our estimate of mu, is 510, and the standard deviation of the sample is calculated to be 91.21. That's our S. Again, we're going to stick to 95% confidence throughout. The critical value we need from the t-distribution with 9 degrees of freedom for a 95% confidence interval is approximately 2.26, and a quick calculation gives our confidence interval with a lower limit of 441.81 and an upper limit of 575.19. This includes 500, the mean of our normal model, and, as we can see, the line joining the lower to upper limits crosses the vertical bar at 500. So this confidence interval was successful at capturing the theoretical mean. Let's simulate some more samples of size 10 and see how the resulting confidence intervals behave. Here we have one that misses a theoretical mean. By chance, for this sample, we got a lot of smaller values, and our estimated mean is only 412, and our upper limit 481.28. So our confidence interval doesn't include 500. For this applet, we can show confidence intervals from 20 samples on one screen. So finishing that up in these 20 samples, the resulting confidence intervals miss the true mean just that once. So our 95% confidence intervals correctly captured what they were supposed to 95% of the time. You might think that was too good to be true. So let's simulate another 20 confidence intervals. This time, we missed the true mean twice. Let's do it again. In these 20 confidence intervals, we didn't ever miss the true mean. One more time, we missed it twice. And another 20 confidence intervals also didn't have any misses. We've just seen a total of 100 confidence intervals for the means for samples of size 10 from this distribution. And if we add up the misses, we missed 5 times, which is exactly what we'd expect for 95% confidence intervals. The t-distribution confidence interval for the mean works extremely well in terms of capturing the true mean as many times as it's supposed to, when the normal distribution is the actual distribution of the data. So let's see what happens with another distribution. We'll switch to the skewed distribution for our theoretical model, and we'll still stick with 95% confidence intervals for the mean, calculated from simulated samples of size 10 from this model. This time, the model mean is 223.1, so that's what we're hoping to capture in our confidence intervals. Our first set of confidence intervals for our 20 samples miss the model mean twice. The second set of 20 doesn't miss the mean at all. The next set of 20 misses twice, and then we don't miss it again, and then again in our 20 confidence intervals, we don't miss the mean. So in our total of 100 confidence intervals, we've only missed the mean 4 times for 96% coverage. Even when the theoretical model from where our data came is not normal but skewed, the T confidence interval procedure works extremely well at covering the mean the right percentage of times. For T confidence intervals for the mean to not work well, we need fairly extreme situations. Here's one, where the theoretical model puts most of the probability on values here on the left, but also makes it possible to see some very large outliers. Our theoretical mean is 83. Let's take a sample size of 10 and check what happens with 20 confidence intervals. We've missed the mean 15 times for a coverage rate of 25%. Certainly not 95%. Of course, the central limit theorem is an asymptotic result. That is, it works better the larger n the sample size is. So perhaps our estimate x bar, the average of our sample, will be closer to normally distributed for a larger sample size, something more than 10. The largest sample size this applet allows is 40, so let's increase the sample size to that, and we'll quickly generate 100 samples. In the resulting 100 confidence intervals, we missed the theoretical mean of 83 10 times, or we covered it 90% of the time. Again, these are 95% confidence intervals, so the coverage isn't quite what we claimed, but it's pretty close. This illustrates how well the T confidence intervals for the mean work, even with this extreme situation and a sample size of only 40. Of course, in this situation, I've been completely ignoring the fact that perhaps estimating the mean may not be a sensible thing to do. Remember that when working with data, the mean or average is not a robust measure. That is, it's affected by unusual observations. When we're talking about the expected value or mean of a probability model, it is also affected by extreme values, in this case pulled up by the large values we could have. And because of these possible large values, the mean of 83 that we got here is actually larger than the possible values on the left where most of the probability is. So to summarize, the T-distribution confidence intervals work extremely well, even when the data aren't normally distributed, but not in situations where it really doesn't make sense to use the mean. This is another illustration of just how powerful the central limit theorem is. Because of it, the T confidence intervals for the mean are extremely robust. In this situation, robust means that they work well, giving confidence intervals with very close to the coverage claimed, even when some of the necessary conditions aren't satisfied. So we have 2 types of confidence intervals for proportions and confidence intervals for the means. Both of them rely on the central limit theorem in order to derive the formula. As we've seen, T confidence intervals work extremely well, even for small sample sizes. However, the confidence intervals for the proportions tend to need much larger sample sizes in order for them to work well in terms of covering the true population parameter as often as they're supposed to. Recall that for both these confidence intervals, we also need all the observations to be independent. And if they're not, the procedures don't apply. In all inferential procedures in statistics, including confidence intervals, it's important to pay attention to the necessary conditions that must be satisfied in order for the inferential procedures to apply. And it's important to understand the implications for the results if the conditions aren't satisfied. Otherwise, we can't really make meaningful conclusions.